All right, we have a 0.1 kilogram object attached to a string and released as shown below. And we're going to say the mass is released at top. This should, yeah. So we want to know the speed at the bottom, and we're going to use conservation of energy. So the idea here is that at the top, we have gravitational energy equal to mgh. And at the bottom, we have kinetic energy equal to 1/2 mv squared. So we're going to set these two energies equal, e.g. will equal ek, fantastic. And so we'll get mgh equal to 1/2 mv squared. And we'll actually put in numbers, so we'll have 0.1 times 10 times this height. Now the height is the total height here, which is double the radius. So that actually works out to be 1.6 meters. That's 0.8 plus 0.8. And that's equal 1/2. That's equal to 1/2 times m, which is 0.1 times v squared. And we'll do some simplification here. So we will end up getting here 1.6 equals 0.05 v squared. We'll divide by 0.05. And when we actually isolate v, we'll actually get v squared equals 32. And v will end up simply being the square root of both, whoops. So v squared is 32. We square root both sides, and v ends up being equal to 5.66 meters per second. Awesome. Now we want to know the tension in the rope at the bottom of the swing. So we've got to be careful here. When we get the tension at the bottom of the swing, let's first begin by drawing a free body diagram of the situation. Because it's very tempting just to say what's, like I heard a couple people during the practice test say, well, what's the formula for tension? And that's absolutely not how we want to approach these problems. What we want to do is draw a free body diagram of the situation where we have a tension going up, and we have the weight pointing downwards, and we have tension minus weight. Whoops. We have tension minus the weight. These forces don't balance because we're accelerating in a circle. So now let's go ahead and plug in our numbers. We've got tension minus the weight, and remember weight is mg. So that's going to be 0.1 times 10, and that's going to give me 1 Newton worth of force. So we'll have T minus 1 equals 0.1 times 5.66 squared divided by the radius, which is 0.8. So just to be clear, the centripetal acceleration is v squared over r. That's going to be 5.66 squared divided by the radius, which is 0.8. And when we solve, what we'll end up getting is the tension should be about 5 newtons. Okay. So if the rope can support 2 newtons of tension, does it break or not at the bottom of the swing? Yes, it does. It needs 5 newtons and only supports 2 newtons. So the tension needed to be supported is 5 newtons worth. As indicated right here in our answer. So that's the second page of the practice test, and we'll take a look at the third page in the next video.